So good evening and good afternoon, or indeed good morning if you're in other parts of the world. And welcome to this Glassinar event. My name is Mauro Overend, and I'm Professor of Structural Design and Mechanics at TUDA. And I'm also a joint editor-in-chief of the Journal of Glass Structures and Engineering, published by Springer. And I'm delighted to welcome you to this third Glassinar event that we have this year. So this Glassinar event is not something I, as probably most of you know, it's not something I organize on my own, but we are 5 joint editors-in-chief, and we're always beavering away and working in the background to organize several things, among which is this event. And you can see us here in an earlier moment a few years ago when the journal was published, and when we were a little bit younger. I think if you see us now, you can see that we're a little bit older already. But anyway, so so the journal, Glass Structures and Engineering, which started in 2016, has been going from strength to strength. And here on the screen, you see all the issues from the beginning until, actually you also see on the bottom right-hand corner, you see a sneak preview of the issue that will be published in the next few days. So you can see there's one coming up. And the other thing I think we take away from this, apart from that, we have now putting rather attractive pictures from the research papers published in each journal on the front cover. But you also see that we had a couple of issues every year in the first 3 years, and now we're up to 4 issues published every year. So volume 6 is from 2021, and we have 4 issues in this year. So there's definitely growth in the journal, which is great to see. And this is only, of course, thanks to the papers that you send to us that are of already such high quality that it's difficult in some cases to it compels us to publish more because of the larger quantity and quality of the papers we receive. We're quite active. Apart from the journal itself, there's many things that are linked and are based on the journal. One of them, of course, is this Glassinar that we're attending today. But also, we are also busy publishing topical issues, sometimes known as special issues, on particular topics. We've actually just relatively recently published one on projects and case studies, and that is available on the journal website. You can have a look at that, or rather kind of very impressive real-world projects. But right now, there's also 4 topical issues which are in the pipeline. One of them is on glass design codes. The other one, as you can see on screen here, glass and extreme events, circularity, and digital transformation, digital fabrication, and artificial intelligence. You will see that from the deadlines on each of these that there is still the opportunity to submit a paper for any of these topical issues. So please, if you have a suitable paper, then please do not hesitate to submit it. And the submission process is in the normal way through the journal web pages and the website, except that in the submission process you will be asked whether you want to submit for a particular topical issue. But as long as you submit it, it will find its way to the right topical issue. Great. Okay. A bit of a reminder, maybe some of you, it's been maybe a few months, and maybe for some of you it might be the first time you were attending this Glassinar. What happens in this Glassinar is essentially that we have about an hour in total. During this hour, there will be two presenters who will present their research and it's papers that have been published in the previous issues of the journal. So far, as I said, this was the first year we've launched these Glassinars, and we've had 3 Glassinars this year. And I think the response and the feedback was certainly very positive, and positive enough that we actually plan to continue these Glassinars into next year. So this may be the last Glassinar of this year, but it certainly, it's not our intention that it's the last Glassinar. So we're already planning the Glassinars for next year as well. Right. So I think that's maybe enough speak from me on the context. Let's get to the subject matter of today's event, which are the talks. We have actually 2 really strong and really exciting talks lined up for you. We have Socrates Angelides, who will be talking to us about his research paper and general research in general, specifically a research paper on the blast resistance of laminated glass. And then following that, we have another talk by Giovanni De Mari, who will be talking about the glass facade in the Typhoon area. It's actually my pleasure to, Giovanni will be introduced later on in more detail, but it's my pleasure for now to introduce Socrates. So Socrates is, as his name might imply, he's originally from Greece, but he studied civil engineering at Imperial College, and was a master's degree there, and then he worked for 3 years, actually as a structural engineer in the oil and gas industry, before eventually in 2016 returning to the to university, where he joined the University of Cambridge to do a PhD in the blast response of laminated glass panels, and under supervision of Dr. Talbot. And I have to say, I also am co-supervising his work, so I know a little bit about it. But he's really developing some really exciting models on the mechanics of failure of laminated glass that could really I think have an impact on and a positive information on how to design glass panels for blast loading. Socrates has also spent some time at TU Delft, and he's now a research associate at the University of Sheffield, where he is working on blast load prediction. And this is a research project between the University of Sheffield and the Steel Construction Institute in the UK. But I think with on that, I think I will hand over to Socrates to present his research.
Thank you very much, Mauro, for the kind words, and also thank you very much for inviting me to present in this third Glassinar. As Mauro has mentioned, this presentation will focus mostly on my research findings on the blast resistance of laminated glass. This presentation will primarily focus on 2 papers of the Glass Structural Engineering Journal, one that was published in 2019 and the other that was recently submitted. At this stage, I would also like to acknowledge the contribution from my sponsors, the Engineering and Physical Science Research Council and the Institution of Civil Engineers. These sponsors have sponsored my PhD, and I also like to acknowledge the in-kind contributions from Kurari, DJ Good and Associates, and Tough Glaze. Renewed focus on the threat posed to buildings and their occupants by terrorist attacks has intensified the demand for blast-resilient buildings. This requires facades to act as a first barrier of defense to protect occupants. However, these are primarily architectural elements and are often inherently brittle, as is the case for glazed facades. Multiple glazing failures were observed in the recent disaster in Beirut, with many damages occurring kilometers away from the explosion source. Consequently, the blast wave penetrated the building interior, resulting in financial damages and harming occupants. Additionally, a large percentage of injuries were glass-related, as is often the case in most blast events. As a result, laminate glass are therefore increasingly installed in facades to enhance the blast resilience of buildings. These composite panels offer residual resistance and are capable of providing resistance beyond the fracture of the glass layers, and also reduce the glass-related injuries as the glass fragments remain attached to the interlayer. The blast response of these panels, however, is complex and often requires assistance from blast testing to validate designs. The starting point in my research was to study the failure mechanisms in laminated glass recorded by previous researchers during full-scale blast tests. I observed a repeated failure pattern that was consistent in almost all tests. This failure pattern resembles the yield line mechanism forming under bending in reinforced concrete slabs. Given the similarities between laminate glass and reinforced concrete, that is, both are brittle materials reinforced with a ductile material, I decided to investigate if this repeated failure pattern in laminate glass is in fact a yield line pattern. To achieve this, I first examined if there's any residual post-fracture bending moment capacity in laminate glass following the fracturing of the glass layers. My second objective was to assess if the effects of inertia experienced by laminate glass panels during a blast event are responsible for the different pattern observed compared to the well-known yield line pattern forming under static loading in reinforced concrete and other ductile materials. Starting with the post-fracture bending moment resistance of laminate glass, previous experimental work on pre-fracture specimens has demonstrated that this is negligible for specimens with polygonal butyryl interlayers. However, these tests were performed at low strain rates, as opposed to the high strain rates anticipated under blast loading. This is important as the PVB interlayer is a thermoplastic polymer that becomes significantly stiffer at high strain rates. The response under blast loading is therefore fundamentally different compared to the previous experimental work at low strain rates. PVB is also sensitive to temperature, and using previous experimental work, I demonstrated that there's a time-temperature dependency similar to many other polymers. Therefore, the PVB response at high strain rates can be simulated with low temperatures by deriving a time-temperature mapping equation. This uncouples inertia effects and allows the investigation of the pseudostatic bending moment capacity. Quasi-static bending tests of pre-fracture specimens were therefore performed at -100 degrees Celsius and were compared to room temperature tests to assess the influence of high strain rates. An idealized pre-fractured pattern was considered with the cracks aligned in both glass layers and spaced every 20 millimeters. Using the mapping equation derived, a maximum PVB strain rate of 25 per second was calculated at a temperature of 25 degrees Celsius, which is a typical value expected under blast loads. A comparison of the load displacement response recorded from the low and room temperature tests indicates a significantly stiffer response at low temperatures. The results of the low temperature test demonstrate an enhancement of the ultimate load capacity of the fractured glass by 2 orders of magnitude compared to that at room temperature. This suggests an improved post-fracture bending moment capacity at low temperatures associated with the now stiffer interlayer working in tension and the glass fragments working in compression. Due to the time-temperature dependency of the PVB, A similar enhancement is therefore anticipated at the high strain rates associated with typical blast loading. Based on the experimental results from the low temperature bending test, analytical models were developed to describe the post-fracture bending moment capacity of laminated glass. Following the initial flexible response until the glass fragments interlock, a linear response is observed and the fractured panel bends elastically in a composite manner. At this stage, the PVB is in the initial slope of its stress strain diagram, and although it resembles an elastic material, it in fact remains viscoelastic. The bending moment capacity was derived for this stage under the assumptions of plane sections remaining plane and by applying the transformed section approach commonly used in analysis of reinforced concrete. The compression component in the bending moment is provided by the glass fragments that come into contact as the panel deforms, and the tension component is provided by the interlayer. A nonlinear response is observed in the next stage due to the change in slope in the PVB material model. Although this transition point is often referred to as yield stress, it only refers to the stress at which a significant change in modulus is observed rather than the onset of true plasticity. A plastic hinge eventually forms when the top glass layer crushes in compression, resulting into a collapse mechanism for the simply supported specimens tested. The moment capacity for this stage is derived by taking moment equilibrium about the plastic neutral axis. In the final stage, the PVB tears when the failure strain is reached. The response, however, is anticipated to be more ductile under blast events, as the low temperature results in a stiffer adhesion bond that inhibits the lamination of the glass fragments and causes brittle fracture of the PVB. The exact same tests were also repeated on specimens with both thicker glass layers and thicker interlayers. An increased ultimate loading capacity and therefore post-fracture bending moment capacity was recorded consistently for all the thicker specimens tested. Therefore, the experimental results were in agreement with the predictions of simple bending theory. To assess if the idealized pre-fraction pattern considered is representative of the random fraction pattern forming under blast loading, the low temperature bending tests were also repeated on specimens with different pre-fractured patterns. The key conclusions of this investigation were that the bending moment capacity is unaffected by the glass fragment size, and it also increases when the cracks are not aligned in the glass layers. Therefore, we can conclude that this idealized pattern will result in a lower bound estimate of the post-fracture bending moment capacity for a specimen with a real random fracture pattern forming under blast loading. Now moving on to dynamic loading, to investigate the effects of inertia, I performed impact tests by launching foam projectiles from a gas gun and recording the response with a high-speed camera. The pressure time history resulting from this impact simulates the positive phase of blast loading. The same specimens, pre-fracture patterns, and span as the low temperature bending tests were considered in the impact tests to directly assess the influence of inertia. Pvb tearing was observed in the smaller cross-section specimens, as can be seen in the lower left video. You can see the tearing occurring right now. On the other hand, the medium and larger cross-section specimens were able to deform under large deflections without the interlayer tearing, as observed in the other two videos on the right-hand side. The same tests were also repeated on intact specimens to assess the transition from the intact stage to the post-fracture stage. In this case, the loading was not high enough to fracture the larger specimens, as observed in the bottom right-hand video. The response of the smaller and medium cross-sections specimens was similar to that observed for the pre-fractured specimens. The deformation patterns recorded with a high-speed camera demonstrate that the theory of traveling hinges applies to laminated glass. A global collapse mechanism with the specimens deforming as two rigid bars and connecting with a single plastic hinge at midspan were observed for the medium and large specimens. This agrees with a well-known collapse mechanism forming in simply supported beams under a static point load at midspan. The same also applies for short duration pulses with a moderate magnitude loading that is less than 3 times the static collapse mechanism. This applies for the medium and large cross-section specimens, as the applied loading, as you can see here, marked as FA on the top right, is less than 3 times the ultimate loading recorded from the previous low temperature bending tests performed. On the other hand, the collapse mechanism observed for the smaller specimen is more localized, and 3 plastic hinges can be observed. This agrees with the theory of traveling plastic hinges when a short duration pulse with intense magnitude loading that is greater than 3 times the static collapse mechanism is applied. This was actually the case for the smaller cross sections tested here when considering the recorded ultimate loading from the low temperature bending tests. These conclusions from the one-way spanning beam specimens are very important, as when these are extended to 2-way spanning planes, it can explain why we observed a different yield line pattern in reinforced concrete when a uniform static load pressure is applied, compared to laminated glass when a dynamic short duration intense magnitude loading is applied to the entire panel. And this is why we see a different yield line pattern. Therefore, these simplified small-scale tests, namely the low-temperature bending test and the impact test by launching foam projectiles from a gas gun, were able to demonstrate that the repeated pattern that we observed from blast tests is due to an enhanced post-fracture bending moment capacity occurring due to the effects of strain rates, and due to the inertia arising from dynamic loading, we observed a different yield line pattern compared to the static loading. The next steps of my research will try to focus on how to complement or improve existing analysis methods or testing methods for designing laminated glass panels under blast loading. Thank you very much.
Thank you very much, Socrates. That was really very well presented and very clear. One thing I should have mentioned before you started, and I then put it in the chat, so hopefully everyone has seen it, is that if the audience has any questions for Socrates, to please put them in the questions box or the questions tab on your screen, and then we can pick them up and put them to Socrates. I see that we already have a question here, and it is the question is about it's actually from Jan Bellis, and the question is, was the minus 100 degrees C an arbitrary choice, or did you try different temperature for equivalent static tests? So how did you get to this minus 100 degrees C, and how
yes, so I think,
yeah.
Yes, so thanks Maro, and thanks Jan for the question. I think the choice of the 900 degrees Celsius was a combination of limitations of our environmental chamber box and actually getting the right response that we needed. So there was a bit of a trial and error until we get the exact strain rate that we needed, but it's essentially we had to modify the temperature based on the constraints of having liquid nitrogen tanks and ensuring that we can reach that low temperature inside the environmental chamber, and also a combination of the displacement rate at which we perform the quasi-static tests. So essentially, we did a few trials of different temperatures and different displacement rates, and eventually we captured a value that worked well, that we could do the tests and the time that we needed, and we could afford to have enough liquid nitrogen, and also get a value of an equivalent mapped strain rate of 25 per second that is representative of a typical strain rate under blast loading.
Thanks, Socrates. We actually have another question from Martin Jensen Mayland, and it's about how you accounted for the strain rate effect and the glass strength.
Yeah, so this is a very good question, and I think you probably were able to follow very well in presentation. We were not able to capture the strain rate in the glass layers, so this was only to capture the enhanced strain rate of the interlayer. So these models will not account for the increased glass compression strength due to strain rate in the glass layers, but only of the interlayer. So we believe that the bending moment capacities are again on the lower end, as the compression strength should be higher under higher strain rates, which was not simulated with this low temperature bending tests.
Right, thanks. I don't see other questions yet, but while maybe we waited, there's another one or two, and we're already kind of running out of time already. I actually have a question myself, and if I understood correctly, you the formation of the yield lines, which you showed a very nice slide. I'm not sure how easy or difficult it is for you to bring up the screen again.
Yeah, of course.
Slide 21, I think it was. Yeah, nice. And you were showing kind of the comparison between the concrete on the left and the glass on the right, and you explained the dynamic kind of dynamic loading. But the actual formation of the plastic, the yield lines, shall we call them that, in the glass, these are to a large extent not a function of the fragment size, right? Or here there's a lot of fragmentation, so the yield line form. So I wonder, I mean, does the fragment size affect the formation of the yield lines?
Yeah, yes. So in my understanding, I think it doesn't. So the under blast loading, you will have multiple small glass fragments in each of your glass layers, and where we see the yield lines is where the glass has actually crushed. So this is a step further. So first the glass will fracture into smaller fragments, and then it will crush at the regions where you have the highest bending moment or the highest curvature, and this is where you see these yield lines forming. So one way of saying is probably the glass fragment size doesn't affect this response, unless the small fragment size results in the fragments delaminating from the interlayer, and then we lose contact. Then this is the only case where I would imagine that the fragment size is important in deriving the bending capacity.
Yeah. Thank you. Thanks. Yeah, and I think to some extent that's the maybe the power of the method that you are proposing, right? That these yield lines actually form as long as you have fragmentation in your glass from some event. Then you can set up this yield line pattern on the glass, which I think is. Yeah. And maybe you can give us a sneak preview or what maybe how could this be? You have already some ideas on how this could be validated in on a larger scale. How would you propose kind of a not necessarily something you might do in your research, but as a follow-on? How could we kind of validate these findings on a larger kind of scale?
Yeah, so I imagine some ways of doing that would be to extending the test to account two-way spanning plates. So either doing shock tube tests with the two-way spanning plates and observing the bending response and seeing if these yield lines will form. I think I've seen some papers that can record the deformation in different timestamps, and you can see the fragment pattern evolving with time. So this is a good start to say that we've seen it in one-way spanning with simple support beams with a point load in the middle. We've seen it with two-way spanning plates with a uniform pressure. So that's a good start to say that this theory of traveling hinges actually applies. The other way would be to start developing methods. I think there are a few. They may need some tweaks, I'm not sure, to be honest, start developing methods of how to calculate the displacement time history, and also comparing that displacement time history with full-scale blast tests.
Thank you. Thanks, Ruth. And I will sneak in one last question from Mark Spiker, and he's asking whether you can simulate high temperature blast and debris together. I mean, so it's a kind of a multi-physics kind of approach, I think is what you.
So high temperature blast and debris together. So probably these low temperature bending tests are not capable of doing that. So I imagine you would need some kind of environmental chamber and a gas can combined together, which
yeah, I think he's asking about simulate whether I think you can capture this in some kind of simulation or calculation, if I understand correctly. It's a simulate rather than.
Yeah. Yeah. So for instance, the impact from debris, I guess I think we could do each of them separately. I don't know if we can do all of them together with a simulation. So if you wanted to combine all of them together in simulation, you would need some kind of gas can with an environmental chamber, and you might damage your environmental chamber. So I'm not sure if that is a good idea. Separately, you could simulate the effect of high temperature. You could simulate the effect of blast, and you could possibly simulate the effect of debris by pre-cracking your glass as you would expect it to fracture under a debris impact, and then doing the test in the environmental chamber. But altogether, I think it would be difficult to simulate all these effects together.
Thank you. Thank you, Socrates. So I think on that note, I thank you again, and the whole audience, although silently, is thanking you as well for your presentation. So thank you very much, and for answering our questions. And
thank you very much for inviting me again.
Great, thanks, Socrates. And I now hand over to my colleague and joint editor-in-chief, Jan Bellis, who will introduce the next speaker.
Thank you very much, Mauro, and also Socrates. It was very enjoyable. So we now jump from Delft, about 180 kilometers to Ghent in Belgium, where I'm a professor at the Department of Structural Engineering and Building Materials. And actually, I have the honor and pleasure to announce the next speaker. You already see him on the screen. Welcome, Giovanni. Giovanni De Mari is actually a structural engineer, graduated from Politecnico di Milano in Italy. He joined the Advanced Engineering Materials and Technologies group at Eckersley O'Callaghan in 2016. And since then, he has been involved in a large number of international projects in different sectors, featuring the combined use of glass and steel, with particular focus on detailing and also innovation. Other than structural glass design, his technical expertise includes also complex geometry design, detailed finite element analysis, and engineering solutions of seismic scenarios. And for the moment, Giovanni is associate at Eckersley O'Callaghan. As the overall team of this Glassinar actually is dealing with extreme events, we have actually a nice fit also with the topic which Giovanni is presenting. Namely, the title of his paper will be a large deflection of glass facade in Typhoon area. So it's the Tycho Place 2 podium wall, which he's going to present. So Giovanni, please share your screen and tell us your story.
Hello, thanks Jan for the introduction and for having me here. So as you said, we're going to talk through the glass facade of the Tycho Place 2 podium wall. So Tycho Place is a 195-meter tall office tower in Hong Kong. with a shape of a rectangular shape of approximately 40 by 70 meters. And you see I've been carried out the design of the whole facade system, so also the curtain wall and the ground floor area. But what we are going to focus now is the design of the podium, which wraps around the four corners, the four sides of the facade. So the design intent from the clients and architect was to have clearly a maximum transparency to show the grace room, how the architect calls this podium area. And different options were kind of taught the schematic phase of the project. So from glass fins to cable wall facade, but nothing was really like going towards the aim and the brief of the facade. So at the end, what we pushed forwards was this kind of hybrid solution, which sees jumbo glass panels, so full height glass panels supported by pre-stressed stainless steel rods, which lies entirely in the buildup of the glass. So they don't add any depth to the facade, and therefore they maximize and kind of the transparency and the shows of the great room, as you can see from these renders from MBJ, the architect. So for the system description, I say the facade was wrapping around all the four sides of the podium, but clearly not with varying height, and therefore not all the areas were needing a pre-stressed cable. So in this elevation of the four elevation of the podium, we show where the pretension facade are. So in this area where the glass is up to 15 meters tall, while all the other area where the glass is going up to 4 meters, the system was a simply supported basically beam spanning from top to bottom. The system itself sees basically an independent set of top and bottom steel structure, which spans between the columns, and the span between the columns can be up to 21 meters in this project, because there are minimal number of concrete column for the primary structure, and the rods are therefore connected to the two beam and spanning top and bottom from the two beams. While the glass is sitting on the bottom steel beam, so therefore the dead load of the glass is entirely taken by the bottom beam, and is clearly restrained laterally for out of plane loads and connected to the rods on the two vertical edges and to the top and bottom steel beam on the short horizontal edges. One of the critical area, probably the most interesting area of the project, was clearly the corner. And this is because of the shape of the facade, where we have this rounded corner, and therefore the interfaces between flat and curved, and then again flat panels. So because of the geometry, because of the high load, we're talking about Typhoon area as mentioned in the title, therefore we got peak of 3.5 kPa of wind load as a characteristic load here. So quite high load, especially for the span of the facade, 15 meters. Therefore, we had to understand a bit better the behavior and how to cope with these different interfaces that we have. What we did was individuating like mainly three interfaces, what we call the typical interface A, which is basically between flat panels, which experience a very similar behavior as the geometry is similar. And then we identified interface B, which is between curved panel. And because of the geometry, the two curved panels will tend to move radially into a different direction. Therefore, they will experience mainly tangential expansion when under suction. And therefore, the joint between the two glass panels will tend to expand. And a slightly different interface is what we identified in the interface C, between flat and curved panel, where because of the two different stiffness of the flat and the curved panel, the two panels will experience not only a differential direction of movement, but also clearly the flat panel being less stiff will tend to deflect much more than the curved panel. So we will tend to cope with some differential radial movement between the two adjacent panels. The way we thought to address this challenge was to define different interfaces in terms of rods and glass connection. So for the position A, the typical one between flat panels, we designed a single rod which clamps the two panels, and therefore, when the panel deflecting the rods is followed by the two panels. What's happening in position B and C, because of this differential radial or tangential movement, what we developed was a system with two rods, which are then only connected by a movement joint. Therefore, they are free to move differentially outside and tangentially. And therefore, the two panels connected and clamped to these to the double rods can experience the differential movement that they will naturally have under wind load. Other key details to cope with the high deflection of this facade and to cope also with the opening that are required in the facade was a rocking portal frame on the main elevation, the east elevation. Here, because of the full height, because the elevation has full height panels for the full elevation, basically, we had to try to reduce as much as possible the stress concentration that we would have had on the two corners of the portal frame, because if the portal frame were to be fixed, clearly the deflected shape would have been very different compared to the one of the adjacent panel, creating a lot of stress concentration. While with the rocking portal frame and providing pin at the base of the portal frame, we try to allow the portal frame to follow much more the deflection of the glass and the rods. Therefore, the portal frame is not independent out of plane because it's not stable, and therefore needs to be restrained back on the side to the adjacent rods. One of the other issues was really to design the bottom detail where the rod anchors to the steel beam. So initially we went for a spherical bearing scenario, although then because of some issue with the approval authority of the specific product, we swapped to an high-end type of rod, which say this kind of fork with a pin, and therefore the further issue on that was to check with the lateral drift if the drift induced bending stress in the rod were small enough to be absorbed. Luckily, the drift limit for the tower designed by the primary engineer was quite strict, so we had deflection of about height over 800, so about 18 millimeter of lateral drift between top and bottom. Therefore, there was not much issue in switching from a spherical bearing to a single plane of hinge like this connector here. And another important things to consider was clearly thermal expansion in the main beam. As I was saying, main beams were up to 21 meter long, spanning between two columns. So thermal expansion or contraction would have generated quite a lot of axial stress in the beam, and therefore, since the beam was eccentric from the RC column, this would have generated massive shear and torsion also on the concrete column. So we wanted to avoid that, and also we wanted to design a connection which was really able to cope with the minimum friction possible to the sliding, and that we kind of took inspiration from some of the lightweight pedestrian bridges bearing, where basically they can act in both directions, so not only in compression but also in tension, and providing some elastomeric bearing on top and bottom to allow to transfer the vertical load, but at the same time allow a quite smooth and frictionless expansion or contraction of the beams. One of the most important things was clearly understanding the wind load of the facade. We started really analyzing the on-call code, and really as something that is mandatory in Hong Kong, a wind tunnel test was conducted. And one of the quite interesting things is that the test, as you can see from these two pictures, was conducted in two different scenarios. One scenario is the current scenario, so where all the building around the building understudies are modeled, and then there is another scenario where all the buildings around the one understudies are assumed to not be there, and therefore this was obviously the most critical one because it gave us returned us the highest pressure and suction on the facade, which in any case were pretty much in line with what we were expecting from just looking at the building code for wind. But together with the wind tunnel testing, as this facade is not really cannot be analyzed as a standalone, it needs to be analyzed on its whole elevation. We did also and feed the wind tunnel test analysis also with some model information of the model behavior of the facade, and trying to understand not only what are the peak pressure and suction to be applied on the wind load, but also on the facade, but also to understand their kind of distribution across the facade and the correlation between pressure and suction in all the points of the facade. So coming from this model analysis integrated with the wind tunnel testing, what we got at the end was a set of load cases. Some of them were like more global, so to maximize in general the wind on some of the elevation, but some other of them were what we call asymmetrical load case, so we're able to maximize some critical interfaces, like for example here on the bottom left, the interface between the last flat panels of east elevation with the first curved panel, or what you can see here on the top right, the interface between the differential pressure between the full light glass panels and the portal frame on the north elevation. So everything was then fed in a quite refined global FEM model, which was used as benchmark to for the design, and was including all the possible components that we could model reasonably for the facade. So not only the glass panels, but and the rod obviously, but also the top beam and the connection, top and bottom beam, and a connection to the RC columns were included. All the portal frames, columns and beams were included as well, and also the connection between the glass panels and rod were simulated by some so-called connection element in the software, which allowed to provide only the lateral out of plane stiffness, which was actually the one coming from the details. And again, here just some focus on the two portals, which have been treated differently. As I was saying, the east one, because of the full light facade, was assumed to be a rocker, so we have a pin connection at the base, and therefore connection back to the tension rod on the side. While the north portal, because of the fact that the facade height goes down quite quickly here, and therefore the different shape of the deformed shape of the facade was slightly different, we could have a simple and normal fixed connection for the portal at that location. In terms of pre-stress value, clearly that was depending from the height of the rod. So the full height rod, the one that are the single rod full height, 50 meter long, were having pre-stress up to 825 kilonewton, while the double rods has a preload range between 225 and 500 kilonewtons for the full light one. In terms of results, obviously we worked with a deflection criteria of span over 60 for the rod. So we were experiencing deflection of about 230 millimeter in the facade. And as you can see also from here, that the deflection coming from the wind code assumed load cases and the wind tunnel one were pretty much in line for some of the load cases. And in terms of maximum axial load or minimum axial load in the tension rod, we had peak of almost 1400 kilonewton for the full light single rod and 800 kilonewton for the full light double rod, while the smaller, the shorter rod under positive temperature and other scenarios which were aimed to minimize the tension, were seeing a value of axial load still below zero. So no rod was going in compression, but clearly with a much smaller margin of value. So you can see here from like 92 to 22 kilonewton for these very specific load case scenarios. One of the important things we had to do was clearly to understand the sensitivity of the glass, mainly to the pre-stress level of the rods. So we studied different scenarios for the rod pre-stress level. So not only the 100% design, let's say pre-stress, but we also analyzed other configuration with 80% of the pre-stress or up to 140%, just to have a load factor equal to the one of the permanent load as per Hong Kong standard. So obviously, it was interesting to understand what was the relationship, which is all obviously not linear. So what we were seeing, especially when reducing the load in the rod, the deflection was increasing, and therefore also some of the stresses in the glass were higher. Therefore, we had to use this basically as a worst case scenario, mainly for the design of the glass. One other important thing was trying to calibrate the tension value and pre-stress value in the double rod, because from one point of view we wanted really to have enough support from the rod to the glass, but at the same time you wanted also to not have too high pre-stress in this rod to avoid having very big differential movement between especially flat and curved panels. So it was very interesting and iterative process to look at these different scenarios and try to balance and fine-tuning the level of pre-stress in these cases. And after we did that, we went through all the load case scenarios and plotted basically the differential movement between two adjacent panels. And from this, we were basically informed by the fact of how much the movement joint between the two rods had to be. So you can see here the diagram with all the load cases plotted against specific nodes to understand the relative movement between the two, and the calculation of how much the movement joint needs to be able to cope and accommodate this movement. From a natural frequency point of view, the code set a limit of 1 Hz to avoid further studies on the facade, dynamic studies on the facade. In the very conservative scenario of just the pre-stress of the cables, of the rod, sorry, then the facade was having a natural frequency of 1.22 Hz, but so above this threshold of 1. But it's worth noting as well that during the wind tunnel testing, as I said before, we had to feed also with some model information. So we were already accounting for some dynamic factor from the basic pressure values coming from the wind tunnel to the more advanced and refined one that we were given when studying the facade as a single element, let's say. For people who doesn't know that in Hong Kong, the composite action of glass is still not like given for granted. Therefore, every time you want to use composite action in a glass panels, you need to do a 4-point bending test. And even if the 4-point bending test returns 100% composite action, you're still limited by a value of 70% of composite action to be used. So because we had to do this 4-point bending test, and because we were asked by the approval authority also to provide some brick models of the flat and curved panels to justify the analysis, we took the occasion of using the 4-point bend test also as a way to calibrate our brick models and show to the authorities that the accuracy of the modeling was quite good. And as you can see here, that this model basically tried to reproduce exactly the 4-point bending test of the glass setup. And all these lines are the experimental results, basically the results from the test, and the straight blue lines. Blue line is the results coming from our FEM model, which is pretty much in line with what the results are. So as I said, we use that basically to validate this brick model that we were requested to do, mainly to understand what was going on this recessed area where the glass flies from 4 becomes 2, to be able to engage in the clamp. And so we had to build also this model. We tried to be very accurate in building this. And we did it for both flat and curved panels. And what we saw from here, which was also something shown by the global analysis, was that clearly the flat panels are very much simply supported, behaving like a simply supporting beam spanning between the two rods, which clearly have then a bit of lower stress here, where the glass is also supported by the top and bottom shoe to the steel beam. while when looking at the curved glass panel, because of the fact that the rods are less pre-stressed, and because of the fact that clearly the glass shape has a better and bigger stiffness also to span from top to bottom, we have a bit more of a typical four-side supported stress distribution, where we don't only have not only have stresses at the center span, but also something going on the top and bottom. At the local model, we had to analyze and build and analyze what the transition between the rectangular shape of the rod when it's interfacing with the glass to this high end for the pin connection at the bottom and at the top, and to study how if there was any risk of stress concentration at this transition area. And also something that was very important that also informed then the global model was understanding the effect of the several openings that we have on top and bottom beam, because of clearly the cable the rod needs to penetrate the beam to be anchored, and at the same time we have other openings on the side and at the bottom to either access or ensure we have space for pre-stressing the rods. And we did with these plates models with openings and without openings to check what were the difference basically for flexural and torsional behavior. What we noticed that really the opening section was having roughly a 10% increment in the flexion, and what we did was just feed this in the global model by reducing the stiffness of the beam model, that's beam element in the global model. I would just want quickly to touch base on also the prove-up process, which was as tough as going through the design of these things. So we started with a pre-submission inquiry, and in Hong Kong there is this the approval authority is called Building Department. It is a quite tough authority to work through, and you know, you need to really justify every single thing, and you can also understand from the fact that you're not allowed to use composite action in glass unless you do test. So the process was quite tough and quite interesting. So we started then with a first PD submission in September 2018, which was rejected with major comments, also depending by the fact that in that time the glass code in Hong Kong switched from one way to another, so there were like some slightly different requirements for the glass analysis. So then we had to resubmit in December of this 2018 as well, and this submission was rejected, but with very minor comments. They were addressed in January, so straight like 1 month after, and finally everything was approved by March 2019. Clearly, there were still like few compromises accepted to ensure that at least in principle the approval was granted, because I should have mentioned that in Hong Kong, from what we know, no large deflection glass facade, even like normal cable wall facade, have ever been approved because of this high flexibility and high deflection. So it's kind of one of the first type of this type of facade ever approved in Hong Kong. So one of the compromise that we had to accept was the one on the clamp between the glass and the rod, which was not allowed to be like recessed and therefore having everything flush with the glass. But although the brick models were proving that the glass was okay, also the centric glass was able to transfer the tension between and the shear transfer between the plies, we had to basically have a clamp from outside, and therefore we had this minimal build-up, minimum depth up on top of the glass thickness. Then some of the images. So in August last year, we started the PMU test on the facade, which really was a requirement from the Hong Kong building department. So you can see here that the module chosen to represent was the corner, because as I was saying, it kind of contained all the critical interfaces, so between flat, curved, and curved glass. And you can really appreciate here the scale by looking at the worker sitting on top of the beam here. So this test was carried out not only to water tightness test, air tightness test, but there was also some structural tests clearly with wind load applied up to 1.5 times the design load. So we were basically blowing up to 5.3 kPa of wind on the facade. Clearly, everything is on site, so it was a bit difficult because of COVID. But luckily, we have also an office in Hong Kong, so our colleague Yanchi has been able to pop up on site from time to time and take some picture for us. So you can see here on the bottom on the left, January 21, facade was tower was going up, and this only the steel beam were almost all installed. Recently in October, you can see basically the concrete has been topped up, and also the curtain wall facade has started to be installed. And you can see here also that the rod has started to be installed, but not pre-tension yet. So you can see here this is the detail of the double rod. You can see the two rod and the gasket between them. And luckily, actually today we had some other picture coming from Yanchi, because the pre-tensioning of the rod has started. So at the moment is one of the first sequence of pre-stressing. So they will pre-stress all the rod up to 50%, then they will move up to 80%, and then 105%. And you can see here the zoom in of the detail at the bottom, where we have the pin. This is the temporary threaded bar for pre-stressing. Another thing that you can see here, probably not very clear from this image, but these things are load cells, because basically one of the requirements was that the pre-stress level in the rods has to be monitored permanently. So we have a set of 4 load cells for each of these rods, constantly measuring the tension and transferring the data to the central monitoring of the building through wireless system. So basically, we have a live prediction and measurements of the tension in the rods, and a warning clearly will be given in case the rod pre-stress and tension level drops below certain threshold or raises above some of the critical value for coming from the design. And thanks.
Thank you very much, Giovanni, for a very nice presentation. I have noticed that there are 2 questions in the question box for the moment. The first one is from Puri Tamarongtam, asking whether you could comment perhaps about the choice between pre-stress or pre-tensioning rod and the cable.
So yes, basically the main driver for going to rod rather than cables was that typically with cables you would have had either a built-in kind of depth of the system. So typically the cable are offset from the glass facade, and then they are connected with clamps across the length of the facade. What we wanted to do here was to minimize as much as possible even this depth. So as you can see from the detail, the rod is basically entirely lying in the buildup of the glass. And actually also because of the shape, which can be a rectangular shape, offers flat surface for having a continuous clamping plate across the full length of the facade. We would have been much more complicated with cable, because probably we would have gone with patch fittings there every certain distance, which was probably not what the architect wanted to see, let's say. So yeah, that was mainly the reason why, just trying to avoid any depth of the system and squeeze everything within the glass buildup.
Okay, thank you. And then there was also a question from my colleague Mauro Overend about the pre-stressing system and the ways how it could deal with possible in-plane movement, for example, caused by either thermal expansion and contractions, or by differential deflections between the floor above and the floor below the glass wall.
So for the drift, basically, the design of the primary structure was quite stiff. So the expected drift we had was about 18 millimeter, which for a 16-meter tall facade was quite minimal. But anything was kind of really what we analyzed this also in the software, so we wanted to really input also the lateral drift movement in the facade, in the primary structure, and the effect of the facade. And clearly, because of that, we basically understood that the glass would follow the rocking against following the drift of the primary structure. And what we were a bit afraid at the beginning was the fact that we had to switch from a spherical bearing connection from the rod to a high end with a pin, which would have generated some sort of bending stiffness and bending deformation also because of the in-plane movement. But because of the very minimal movement and the fact that at the end of the day also the stiffness compared to the height was very minimal, the rod was able to absorb this in-plane movement. And that's what also then tested in the PMU, because also in that case we had to set the facade with the drift, and everything was basically as coming from the results of the model. So that was mainly the way to tackle it. And remember, the first part was about the question.
Well, the first part of the question was about also the pre-stress system and how it deals with in-plane movements caused by thermal expansion and contraction.
So the pre-stress system, is basically everything is going to be tensioned by the bottom connection. So probably I may share again the screen if you don't mind and show the image. Probably this one is a bit better. So what we allow here is an opening, a threaded opening for a bar to be slotted in, coming from this other opening we have at the bottom of the flange. So once the bar is threaded, then it's connected to a hydraulic jack which push against the bottom flange of the beam. And once everything is locked in position, we can insert a shim to lock the position of the rod and the pin, and also add these bearing bolts, which will be threaded against this steel block, and will clearly bear against the top flange of the beam to lock in position the rod and keep the pre-stress.
Okay, great, thank you. There are a few extra questions which have come in meanwhile. However, I think I have to keep an eye on the timing as well. So what I propose is that we actually try to or we ask you, Giovanni, to answer these questions maybe in a written way in the question answering section. We could also do that maybe after the official part of this presentation. Okay, good. Thank you very much once again. I would like to invite now Mauro perhaps to share his presentation again, so that we can move to the final part actually of this Glassinar. And that will be about, let's say, a prize which we are actually offering from the journal Glass Structures and Engineering. So based on the papers which have been published in 2020, there is the prize for the best paper, which is called the Best Paper Award 2020. And I would like now to give the floor to Ms. Nathalie Jacobs, which is executive editor at Springer Nature, responsible also for our journal. So Nathalie, please, floor is yours.
Thank you, Jan, for the introduction. First of all, I would really like to thank the speakers. Your talks were really great. Thank you so much. Yeah, now we have come to the moment that we are announcing the 2020 Best Paper Award of the journal Glass Structures and Engineering. And I'm announcing it now. I would like to congratulate Telesila Ristogiani, Vedra Economopoulou, Ron Yu, and Rob Nijsse with the paper Investigating the Flexural Strength of Recycled Cast Glass. We would really like to congratulate you. And yeah, congratulations, you will get a certificate and you will get a year free access to the journal and a €100 book voucher for Springer.com. You will receive that from us in an email tomorrow. I would like to encourage everybody else to submit your paper to the journal, and then who knows, next year you are the best paper award winner. Thank you all. Mauro? Yeah.
Well, thank you very much, Nathalie. Of course, congratulations also go to Fred Veer and the whole team. So it's yeah, very nice that you have won altogether this award. Well, I think we can now close the official part of this third Glassinar. Thank you very much to the speakers, also to all attendees for attending, and we hope to see you back normally in spring of next year. Thank you very much. I would like also to ask the speakers to stay with us for a little longer. Thank you. Bye bye.